Greetings, I'm Prashant Kamath, Professor of Chemistry and Biochemistry and Radiation Laboratory, University of Notre Dame. We recently published a perspective in the Journal of Physical Chemistry Letters highlighting some of the applications of graphene-based assemblies in energy conversion and storage. Graphene, as you know, is a two-dimensional carbon sheet. This material possesses some very interesting properties that can be used in nanotechnology applications as well as energy conversion applications. Here at Notre Dame, we are focusing our research on finding ways to utilize these graphene sheets more efficiently. In order to make these graphene sheets available in solution so that they can be processed chemically, we take graphite powders, then oxidize by using various oxidants and suspend them in solutions. This method is known as Hummer's method and is very convenient to get graphene sheets in solution processable way.
Next, I want to talk a little bit about monitoring electron transfer within these graphene oxide systems, and specifically the reduction of graphene oxide using colloidal titanium dioxide nanoparticles. So we start with a solution. It's a 10 millimolar solution of TiO2 nanoparticles. Now, if you seal it and purge it with nitrogen and get all the oxygen out, this is in ethanol, and you stick it in front of UV illumination, you can get this blue color. And the blue color represents stored electrons at defect sites on the TiO2 surface. Once we've stored the electrons in the TiO2 nanoparticles, we can titrate them using a dispersion of graphene oxide. And as we add the graphene oxide, we see the color begin to change to a gray color. So you see the blue color slowly fading away, and the gray color indicates that the graphene oxide has been reduced. So at this point, you can add silver ions to the mix, and any stored electrons in the reduced graphene oxide will then be transferred to the electron accepting silver ions. So to the gray solution, now we will add some silver ions, and we should see the gray color turn this ruddy red, reddish brown color, indicating that the silver ions have been deposited as silver nanoparticles on the reduced graphene sheets. So you can selectively deposit a number of metal nanoparticle catalysts on the surface of your graphene sheets using this process.
So now we take these solutions and then modify them with semiconductor particles and metal particles. That way we can generate photocatalyst systems or develop into electrodes that are photoactive. Typically we use semiconductor particles like titanium dioxide, zinc oxide, cadmium selenide. These materials, when they anchored on the graphene sheet, can absorb the light and transfer the electrons into the graphene sheet. The graphene sheet thus becomes as a collector and a carrier of electrons to give you higher efficiency solar cells.
Hi, I'm Kevin Taverdi, a fifth-year graduate student in Prashant Kamath's research lab. This is Dr. Hwangbong Choi, a visiting scientist from Korea. And we are going to talk about how specifically we employ graphene-based materials into photovoltaic devices. This is the setup we use to characterize such devices. It is a xenon lamp which passes through a global AM 1.5 filter which simulates the solar light at the surface of the Earth. When we allow that light to interact with one of our photovoltaic devices, we see a clear photocurrent response with time. If we turn it off, the photocurrent response goes away. Now this sort of setup is employed by first taking a conductive glass electrode on top of which we can put the graphene or carbon-based material. Now we can make that material sensitive to the sun's light by adding a solar sensitizer such as cadmium selenide quantum dots. Here the orange color comes from the cadmium selenide quantum dots. If we want better efficiency or a higher performing device, we can employ what is called a sandwich solar cell, which brings the working electrode and the counter electrode in very close spatial proximity, which allows us to get better performance and more mimic what a real-world device would behave like.
So this is just the beginning of a very exciting field of research in which graphene will find more applications, and the scientific community is right now addressing these issues.